Okay, picture this. A huge warehouse, aisles just stretching out into the dark, and right in the middle, a robot freezes. To its left, there's a charging station. To its right, the package it's supposed to deliver. But here's the thing, its battery is low, and a brand new high-priority order just pinged its system. Suddenly, it's staring down 1,000 choices, a million ways to fail, one wrong move, and the whole operation just grinds to a dead stop.
So how in the world does it do it? How does a machine, faced with all that chaos, make a decision that isn't just good, but perfect, thousands and thousands of times a day? Well, that's the mystery we're going to unpack. We are going to take a peek inside the mind of a robot and find the beautiful, elegant logic that turns all that chaos into perfect clockwork.
You know, for years, the answer looked something like this. It's called a finite state machine. And yeah, it looks like a tangled web of boxes and arrows, because that's pretty much what it is. Each box is a state, like move to object, and every arrow is a choice, like is the battery empty? And look, it works for simple stuff, but as soon as you add more possibilities, what if the object isn't there? What if the loading bay is full? This whole web just explodes into a total mess. They call it the state explosion problem, and trust me, it's an absolute nightmare for programmers.
But that tangled mess, that nightmare of complexity, that is not the end of the story. What if we could just throw it out? What if we could give the robot a clean, clear, elegant map to navigate its world instead?
And this is that map. It's called a behavior tree. Now I know, at first glance, it might look a little complicated, but this is the elegant solution we've been searching for. This is our map to the robot's mind, and we're going to explore it piece by piece, node by node, until its logic is totally clear. We're going to keep coming back to this map as we uncover each part of the puzzle.
So how does a map like this come to life? Well, it all starts with a single, repeating signal, a constant pulse that drives every single decision the robot makes. That pulse is called the tick. It starts way up at the top, at the root, and it travels all the way down through the branches, asking every single part of the tree, hey, what's your status? What are you supposed to be doing right now? And this happens incredibly fast, maybe 100 times a second. It lets the robot constantly check its world and react instantly. It's the tree's very own heartbeat. But what if one part of the tree, say way over on the left, needs to tell another part way over on the right something important? Like, hey, I found the package at these coordinates? Well, for that, they have a shared brain, the blackboard. It's just a central memory space, like a big whiteboard, where any node can jot down information or read what other nodes have written. It's the communication hub for the whole system.
And right here, this is the perfect example of the blackboard in action. See that little label there? The check number nodes, their job is to write a value to that label on the blackboard. Then later, a completely different node, publish result, comes along and reads from that exact same label to get the info it needs. It's a totally seamless way to pass data around, all thanks to that shared memory.
Okay, so our tree has a heartbeat and it has a shared brain. But how does it actually, think? How does it make decisions? Well, that's the job of the control nodes. These are the managers, the strategists that really dictate the flow of logic through the entire tree. Our tour of the brain starts right at the top with our first type of manager. See this node here, the one with the little arrow icon? That's a sequence node, and its job is to make sure things happen in order.
A sequence node is like a super strict checklist. It basically says, do this, then you have to do this, then you have to do this. It just goes through its children from left to right. If every single one of them succeeds, great, the whole sequence succeeds. But, and this is key, if even one of those steps fails, it stops right there, immediately, and it reports failure. It's for those tasks where the order is absolutely critical.
But, what happens when things don't go according to the plan? What if you need options? Well, for that, we turn to our other kind of manager, the fallback node. You can spot it by the little question mark. Think of the fallback as the backup plan node. It tries its children one by one from left to right, kind of asking, can you do it? No? Okay, how about you? Can you do it? The very first child that reports success, that's the winner. The fallback immediately stops and reports success all the way back up the tree.
It only fails if every single one of its backup plans fails. This right here is what makes the robot so resilient.
So we've got the managers, the control nodes, telling the tree how to think. But who's doing the actual work? Who's moving the arm, or driving the wheels, or checking the sensors? Well, that would be the brawn of the operation, the action nodes. So let's follow that chain of command all the way down to the leaves of our tree. See this little box here? That's an action node, one of the real workers of this whole operation.
Action nodes are the doers. They could be anything from pick up the object to calculate a trajectory. And when that tick signal reaches them, they report back one of three things. They can say success, which means I did it. They can say failure, meaning nope, couldn't do it. Or, and this is so important for complex jobs, they can say running, which means, hey, I'm still working on it, check back with me on the next tick.
Now, there's one more special type of node we need to talk about. See this one right here? It's called a decorator. Notice how it only has one child. It's not really a manager and it's not a worker. It's something else entirely. These are decorator nodes, and I like to call them the rule benders. They basically wrap around a single child node and just change its behavior. This one is a perfect example. It lets its child run, but no matter what the child says, success, failure, doesn't matter, this node turns around and tells its parent, everything's great, it was a success. It's a clever way to bend the rules of the tree's logic when you really need to.
Okay, so we've mapped out all the theory, but this isn't just some abstract idea. This is the exact logic that's being used inside some of the most advanced robotic systems out there, like the really popular ROS2 framework.
And this just brilliantly shows the point. On the left, you've got our simple number checking example. On the right, that's a real behavior tree telling a physical robot to move to a location using ROS2. But look closely. It's the same structure. You see that sequence node that first waits for a server and then calls the action? It's the same fundamental building blocks we just learned being used to command a real robot in the real world.
So here's the really crucial takeaway. Because an action node can report back running, the robot can start a long task, like navigating all the way across the warehouse, without freezing up its entire decision-making process. The tick just keeps flowing, which lets the robot handle other checks or react to new obstacles, all while that big navigation task is running in the background. This is what makes these behavior trees so incredibly powerful for real-world robotics.
So, let's come back to our map one last time. We started with that state explosion problem, that tangled, awful web of logic. And now, we've arrived here, a structured, readable map built from really simple parts, a heartbeat tick, a shared blackboard, those strategic control nodes like sequence and fallback, and the hard-working action nodes. This isn't just code, it's a blueprint for smart, resilient behavior.
We've seen how this brilliant map works in a nice, controlled example. But what happens when you let it loose in the real world, with all of its chaos and messiness and unpredictability? What happens when a sensor fails or an obstacle just appears out of nowhere? That's when the real test begins. And that, well, that's a story for our next explainer. Ariar.